The point of this assignment is to be sure we understand when the chain rule is required and when it is not. So in each problem, one of the two requires a chain rule. So we look for the glob within a glob. So our first problem is just 7 to an x whenever we have x alone. That's your clue that you do not need to do a chain rule, as opposed to the second one has a linear function as its exponent. So when we do the derivative of 7 to the glob, we would do the same thing we did a minute ago. We would do the 7 to the power times the natural log of 7, but then we have to remember to do the chain rule on that glob. So the chain rule on the 3x plus 7 is just a 3. So then, of course, we could bring that 3 out in front of the entire thing, but there's not much we can simplify here. Ln of 7, of course, is just another constant, so I guess maybe you might write that in front here. Have the constant in front of the term with the variable. Doesn't really matter. All right, and in question 2, looks a little bit more complicated, but again, here we see x stands alone, as opposed to here we've got a function that has its own derivative. The derivative of x is just 1 in the a term, but the derivative of 4x is 4 in the second term. So both of these require a product rule, however. So we're going to take the first term times the derivative of the second term. So the first term, that's our u, and then we've got to do our v prime, and the derivative of that second term there is 4x to the third, plus our v term times u prime. So x to the fourth times the derivative of e to the x is still e to the x. So I would ask that you always, in these problems, bring the e to the x out as a GCF, and then the two remaining terms, we might swap them so that they're in order from highest power to lowest power. And now in part B, we're going to do the product rule again, but now it's not quite so simple. Now our u glob is going to require a chain rule within it. So we've got to be very careful here. So we're going to take our u term and leave it alone, and then multiply by v prime, which again is 4x cubed, plus, and now our v term, leave it alone, times our u prime, and this is where we require the chain rule. So the derivative of e to a glob is e to the glob with a chain rule on the glob. So the derivative of the 4x is 4. So this now changes our GCF a little bit here. So we see that both terms have an e to the 4x, both terms have a 4, and both terms have at least an x cubed. So 4 x cubed e to the 4x can come out of each term, and from the first term all that's left is an x, and from the, oops, I took out x to the third, sorry, from the first term all that's left is a 1. From the second term what's left is an x. There, I think I did that correctly. All right, let's take a look at question 3. Which one requires the chain rule? Here we have x all by itself as our inner argument, but here our inner argument, 3x, has its own derivative of 3. So when we do our y prime here, we're going to do the derivative of the outer function is negative sine of the same glob, and then the chain rule on the glob is a 3. So once you're used to doing these, you'll just put that 3 out in front right away. You'll think of the chain rule immediately when you see these. And our second one does not require a chain rule. You could say, well, should I do a chain rule on 1x? You certainly could. Notice it wouldn't do any harm. The chain rule, the derivative of x would just be a 1. So I've seen some students say they're always going to do a chain rule to make sure that they don't forget any of those. All right, and we've talked about enough trig terms here that I hope everyone gets the idea that when it comes to derivatives, it's unfortunate that our exponent isn't on the outside of parentheses. So this notation is a little unfortunate. So remember that the squaring is actually the outside function. So here our cotangent is the inner glob, and our outer function is the squaring function. And in 4b, we just have the cotangent function. So of these two, certainly the one that is quicker is 4b. The derivative of cotangent is the opposite of cosecant squared. No chain rule required on b. On 4a, we have a function inside of a power rule. So here we would do the power rule on the outside and bring this exponent down to a 1, which I'm going to erase because later you might think that that's a prime symbol. And then we're going to do the chain rule. Whoops, not yet. We're going to leave the inner glob alone. Sorry. Leave the inner glob alone. And then we're going to do the chain rule. Multiply by the derivative of cotangent. So there's a cosecant squared x. And should we rewrite this, and how should we rewrite it? Well, putting the negative 2 out in front, and then when we have a monomial, it doesn't really make too much difference how we write this, but you might do lowest to highest power a little bit different when you have a monomial. All right, and then you've seen this cartoon before, probably one of the most common jokes or repeated comments in calculus. How's my deriving? So hopefully your deriving is going well. You really do have to have very good techniques of doing derivatives because we'll use them all year long. All right, let's take a look at 5. We do not have anything with a function inside a function. We just have an x inside a cosecant. And our second one, notice this is not the cosecant that is squared this time. This time that 2 applies only to the x. So we could put parentheses there. That 2 applies only to the x term. So this is the one that has a function inside of another function. So 5a does not require a chain rule. The derivative of cosecant is negative cosecant x, cotangent x. And for 5b, think about your order here. So we do the outer function is cosecant. So we'll do negative cosecant. Let me just scroll here. Negative cosecant of the same glob, cotangent of the same glob. And then we do our chain rule on that glob. So when we do the derivative of cosecant of a glob, we get negative cosecant of that same glob, cotangent of that same glob. So remember not to change these arguments until you get to the chain rule. And then we can bring that out in front. So you can think of doing that chain rule one step ahead of yourself in the future. That would save you one step of writing. All right, and let's see what we've got for 6a and b. In 6a, we have the entire parentheses squared. So we have a cubic function inside of a quadratic function. As opposed to 6b, each of the terms is simply a power rule individually. So in 6b, I can just do the power rule, and I'm finished. You could factor it. When it's just this binomial, factoring doesn't save you too much, but when we're looking for zeros later on, you might get in the habit of factoring your derivatives, but either one of those would be acceptable. In 6a, first thing we want to do for our derivative is our power rule. So we want to bring the 2 down in front. 7x cubed plus 3x stays the way it was, and now we're down to the first power. And again, I'm going to erase that so it doesn't look like a prime symbol to you later. And then we do the chain rule on our inner glob. which is a 21x squared plus 3. And then we can look to see if there is a GCF of any of these, and this term right here has a GCF of 3. So we can take a 3 out of that function, and from this one we have an x that we can bring out of this function. We can bring an x to the outside. So remember, we can do that only because this is all multiplication. There's no plus sign here. So we're going to bring a 3 out of one parentheses and an x out of the other. So we would have a 6x now out in front. And we'll have a 7x squared plus 3 times a 7x squared plus 3. So should we rewrite that? And it looks like I have a factoring error here. Notice I took a 3 out of a 3, and I didn't change that. Let's make that a 1. All right, now I think I like that answer better. Okay, let's look at this problem a second way. Let's look at a second idea here. Since we're good at foiling, multiplying, go back to the original, and let's take this binomial to the second power. So we would have 49x to the 6th. Our outside-inside combinations would both be 21x to the 4th. So that would give us a 42x to the 4th and a 9x squared. And then if we did y prime, if this were a 6 times 50, that would be 300. So I guess this should be a 294. X to the 5th when I do the power rule, and a 168 x to the 3rd, and an 18x. And now I'm curious whether we've got the same answer, so I think 6x is a GCF here. So I can take the 6 back out again. 6 into 128 would be a 28. X squared and a 3, and then we can check our factoring here, and let me give myself a little bit more room here. I kind of just messed up the position of my window here, but I think we're okay. I want to factor this into 2 binomials and show you that we get right back to the previous. So both methods would work there. So I think the using the power rule and the chain rule was a little bit simpler. Here I could have foiled and then gotten the form of the answer here as the derivative. All right, and question 7. Which one requires a chain rule? Here I just have a 1x inside the tangent function, but here we have a linear function inside the tangent function. Both of them require a quotient rule. So to find y prime, I'm going to do low d high, and by the way, you could bring that 2 out of the numerator and put it back in at the end of the problem. Depends which you like. Or you can just keep that 2 with the numerator. So if I do low d high, the derivative of the numerator would simply be 2 secant squared x minus high 2 tangent x times d low. The derivative of e to the x is still e to the x. And low squared would give us an ex squared, and I know I can cancel one of those, is why I wrote it that way. So we can factor an e to the x. We could factor the 2 out and get right back where we were before if we had kept the 2 out in front. So completely your choice. And one of these e to the x's will cancel. So if I write it that way, I've seen students just cancel out that exponent of 2. So to be clear, this is what we have left over e to the x. And our second quotient rule is the one that requires the chain rule. So let's work that a little more carefully. will be similar. So we'll have our low function. And now our d high function is going to take a little bit more space because first the tangent of the glob has a derivative of secant squared of the same glob, and then times the chain rule on that glob would give us a 2 here. And then minus our high function, sorry, other way around, our high function, leave it alone, times the derivative of the low function is still our e to the x, not ex, but e to the x, all over our denominator squared. So our e to the x is still going to factor out of the numerator and cancel. Is there anything else that cancels up there in the numerator? Not really. So I could just rewrite it. And then in our denominators, if you prefer splitting that up, for example, to show your canceling, and I think that's clean enough, I would be able to read your answer. But I suppose I could be precise and rewrite it. So I hope you could tell which of each problem required the chain rule and which one did not. But I think we're all set there. That's the end of it.